No, this says Microsoft Teams now. So we're going to take a slightly different approach. We're not going to use sample data to begin with. What we're going to do is we're going to invent our own data. Okay? And so this is going to be something that we'll cover a little bit more detail later on. But YT has a number of different mechanisms for loading data from disk, from in memory, providing function handlers, and so on and so forth. And so the very first thing we're going to do is we are going to create an array of random data. We're going to use, we're going to import YT. We're going to import NumPy. And I'm going to create a random array. And we'll start out with something reasonably small, like 64, 64, 64. And so we can look at that. And you'll see that it is random. I think it's uniformly distributed, not a normal distribution. So it should be, roughly speaking, completely distributed between 0 and 1. And what we'll do is we are going to utilize a function called load uniform grid. And so this will let us talk a little bit more specifically about how fields that exist on disk function and how fields that exist in memory function. So we're going to start out by saying load uniform grid. It takes a couple different arguments. This is a little bit rote, but bear with me. We will assign this to the density variable. And so in doing so, what we're doing is we are imagining that we are creating a uniform grid, or that we are creating a data set that only has one field, and that field is density. This is not realistic typically for simulations. Typically, you'll have any number of different fields. It is a little bit more similar to things like some types of medical imaging where there's just activation or something like that. There's just one signal. It might be similar to pre-fused data from like multispectral imaging of crop cover, things like that. I'm sorry, I'm from the middle of a cornfield, and so like everything goes back to freaking corn with me. We're going to create that. We also have to supply a couple more pieces of information, and it's possible I will get this order of arguments wrong. Mirroring my screen, I can't have my notes up, so I am truly without a net here. We specify our dimensions. And then we also specify a bounding box. Okay. Now, Ramil's not here, so I don't have to talk about units. But we can, in this, also specify units. Do I have this correct if I say array? Is that the correct order, or is it units and then? So here I am specifying my array in grams per centimeters cubed. And then I can also say length unit equals cm. Really, I'm without a net here, though. So let's review this. DS, load uniform grid. I'm providing just one field this time. Yeah. Yeah. Let me see if I can do that in a way that it doesn't. Here, let's go here. I go to advanced settings. I go to theme manager settings, 24px. Let's try 32. Is that better? Okay. All right, so now I will execute. Oh, Specify B box equals and dims equals. We'll just become. There we go. Okay, so we'll specify B box for bounding box, and we'll specify length unit as cm. So just to review, we specified density, it's this array. We specified this is the units that it's in. It'll turn it into a unit array magically for us in the background. Here, let's all practice. Not one person. For those of you watching the recording, one person did it. We say that it's 64 cubed, and that might look a little bit redundant, and in some sense it is. However, for consistency's sake, there are situations where the bounding box is not the same as the uniform grid, or the dimensions of the base level are not the same. For all purposes that we'll be into this week, they are. We've got a bounding box of an array that goes from 0 to 1 in x, 0 to 1 in y, 0 to 1 in z, with a length unit in centimeters. And so that means 0 centimeters to 1 centimeter, and so on and so forth. So now we've got it. And if we look back at some of our parameters, remember we talked about the parameters array, you'll see it generates a couple for us, but it also has domain width in one code length, which in this particular case is also equal to centimeters. Or if we wanted to look at that in the radius of Jupiter's, it is 1.43 times 10 to the minus 10. Yeah.
Sorry to interrupt, but I did wonder with this kind of the nice drop-down menus, is there a way to access all these units without basically going through
Yes.
drop-down menu just direct? Okay.
Absolutely. The reason that, so if we do domain width, okay, so domain width itself is like a special thing. And so and it will display it like that. But if I were to do array equals, no, I don't want to do that. Array DW equals domain width. And I type DW.copy. There we go. So you can see all the different units that are available by doing unit registry.keys. Units.keys. Registry. Okay, well, there is a way. Nobody's chiming in to help me out here. Okay. In general, yes, there is a way. I can't remember what it is. The dropdown is a very special case that happens for things like ds.domain width. There's also domain left edge.
You can do ds.unitregistry.keys.
ds.unitregistry.keys. There we go. And so these are all the different ones. Not all of these will come up with the length dimension. So the way that unit works, and I can't remember if you explicitly said this, but each one is associated with a different collection of dimensions. And so there's the length dimension. And so any attempt to convert them into something that doesn't have the right length dimension, so like if I were to do dw.in units, let's say Kelvin, it'll say, wrong dimensions. Cannot convert between code length, which is dimension length, and Kelvin, dimension temperature. Okay. So we've got our DS here, and it's composed of just our random data. If we look at ds.fieldList, this is the set of on-disk fields. In this sense, even though we call them on disk, even though they're strictly speaking just in memory. This key, as Britton mentioned, typically the on-disk fields will be keyed to the name of the front end and then the name of the field. In this case, it's what's called the stream front end. And now if we look at ds.derived field list, you can see that there are actually a ton of fields that it already knows. So here's the way that YT thinks about these fields. There are a set of field plugins. Each of these field plugins gets called with the collection of fields that are available. anything that it can successfully generate gets added to your field list of derived fields. So for instance, it knows how to, using cell mass, using the cell width, you can multiply the cell volume. You can multiply the cell dx, dy, and dz and get the cell volume. Multiply the volume by the density and you get the mass. So it knows how to turn density and length into mass. And so it does. So just with density, it will add on a ton of these fields. In fact, for some fields, not all, but for some fields, it will automatically add a gradient function. So if I were to access density gradient x, it is a scalar field that is the x component of the gradient of density. Density gradient magnitude, of course, is the magnitude of the x, y, and z components. And so with just this, I mean, like it'll do dynamical time, which I think that might be you. You might have done that. It will be able to compute these different things. So one other thing that we've kind of stepped over and not talked about is that YT has the concept of index space and spatial space. Index and space. And in index space, we have things like dx, dy, and dz. But in space, we may have different length elements associated with them. So for instance, the path element along z may not be the same as the length element in index space along z. And that shows up typically in things like d theta, d phi, dr, because in those spaces, your path element along the theta is, for instance, dependent on the r, right? So your path element is different than d theta. Okay, so these are all the different fields that it knows how, that it thinks it knows how to generate, given just this set of on-disk fields. Now, there's a little bit of overlap here. Index fields, as Britton mentioned, typically refer to things that are related to the spatial location of things. They often get duplicated into density or into your gas fields. And then the stream fields are ones that are, inherent to the data set. So Britton alluded to this, but if we look at ds.fields, and here I'll have to zoom in, this will show you in a tabbed little environment if you have IPy widgets installed, which I think, broadly speaking, comes with most Conda installations of Jupyter and whatnot. Here it will show you the source function for each one of these fields divided up by the individual fields themselves. So some of these things are definitely internal code values. Like here, translation func, like that's weird. What does that mean? Right? It's some internal value. But if you look at something like the gas cell mass, you can see how it generates it. You'll see it generates it by defining a field that takes a field and a data object, and it returns the density times the cell volume. There are some other things in here because we can have multiple field types. So you can look at the variables area, and it shows you what each one of these variables is defined as. So if we look at cell volume, for instance, here, data, field name, copy. Here, field name is index cell volume. And so it becomes slightly more useful in that sense. So this is interesting in the sense that what happens when YT loads a field or loads a data set? Upon indexing, it collects all the fields that are available on disk, and then it runs through its collection of plugins to determine what derived fields can be made from them. This includes things like magnetic fields. And so if you do magnetic fields, if there are magnetic fields in there, there will be a certain set of fields that pop up from that. It includes things like gradients and divergences in some cases, but it tries to add all these things up. I'm going to show you the source code for just a moment so that you can see what this looks like for something like magnetic fields. So we generate a set of magnetic fields, and then what it does is it attempts to infer information about the physical constants that the magnetic fields rely upon, whether or not there needs to be like a 1/4 pi normalization or something like that. And then it attempts to add different pieces of information, dividing by the appropriate dimensions and so on and so forth. So if it's able to, it'll even compute a plasma beta, it'll compute magnetic pressure, and so on and so forth. Oh, and I see we've got a match statement here. Yeah. Peace. Yeah, peace. Yeah. Or computing these things in different coordinate systems. But ideally, for the most part, these things don't need to be modified unless you have very specific use cases. The other thing to keep in mind is that derived fields are always backups. Okay? So some simulation codes might compute on the fly things like divergence, curl, gradient, any of that stuff, and then output them as a specialized field. Okay, so Gamer does this, Enzo can do this. I don't know if Flash can do it, but a lot of these, and I know Arepo has a number of different derived fields that it dumps out into the file. Anytime that something like density gradient magnitude is found in the file, it supersedes the derived field. The assumption is that what comes out of your simulation code is closer to the ground truth that you are interested in. So one specific case that this has come up in the past, let's take Enzo as an example. Enzo does a triangle-shaped, or can do a triangle-shaped cloud interpolation, although I think it usually does particle and cell or something like that. For cloud. Yeah, particle cloud, yeah. Cloud and cell interpolation for dark matter particles to dump them onto the grid, okay, in order to compute a density field. It does that in a way that is somewhat idiosyncratic. There are slight differences if I were to attempt to do it here because of the way that the place and the time step that Enzo does it or something like that. So if Enzo has output temperature or dark matter density or something like that, YT will not override it. It will utilize what is closer to the underlying ground truth. There are other reasons that this can be important, like sometimes you want to make sure you're using the correct value for ghost zones or anything that requires a stencil, and sometimes you want to be as close to possible, or close as possible to the underlying simulation code. So we've got these fields. These fields are first class. They all work just like your other fields. So for instance, DSR gives me all data, and then I can access from it something like cell volume. This is a derived field, but as Britton noted, it shows up just as though it were a regular field. One big difference is that typically the derived fields will come to you in whatever unit system you use. By default, it's CGS, but you can specify MKS at load time and things like that. There's MKS, there's a couple others. I think there's like a whole cottage industry of electromagnetic unit systems that you can utilize, as I recall. Anyhow, that's a good startup idea. You are probably going to get to the point where you want to create your own derived field. So for instance, I am an amateur paleontologist. And I've actually done a fair bit of work on sort of the mechanisms of computing the rate of dinosaurs. And it turns out that you can approximate the rate of dinosaurs in any fluid parcel by taking the density and multiplying it by the temperature. So I want to create a dinosaurs field for my data set. And I want it to be the density times the temperature. Okay? So let's go back up. Hey, Britton, later you can tell me if you think my jokes aren't landing or if I'm just not. So I'm going to create a new array. I will call it array 2. And I'm going to put array 2 here. And we'll say that it's in units of Kelvin. Okay. So now I've created this new data set. And actually, if I look at fields again, see now there's temperature. We've even got KT. It'll compute a genes mass for you. That's pretty rad. And you can see all the source for how it does the genes mass. It's too small here, I know, but now I want to compute the density times the temperature. And as we saw earlier, we could do that by doing dd equals, and this was Corrington's talk, ES all data. Yeah,
Aha. Today was tuples.
yeah. There we go. Sometimes by design, it's possible to have the same field name in different field types. And I think this is something we've kind of elided a little bit, but the tuple refers to the field type and then the field name. And in any case of ambiguity, it will complain at you. So here I've done dd gas, or dd gas temperature times dd gas density. And so this gives me the result that I'm looking for. Okay, just to be totally clear. But it doesn't take advantage of any of the things that Corrington mentioned, for instance. If we were to do something like dd dot mean dinosaurs, it can't do it. It doesn't know how to compute the dinosaurs field. So what we want to do is we want to create a new derived field. Derived fields are defined by the functions that generate them. So this is it's a little bit of a different way of thinking about things, at least from my perspective. What we need to do is we need to write a function. So I'll call this function dinosaurs with an underscore at the start. And they always take the same arguments. They take a field and data. Now here's why we have to write them this way. Data here is unspecified, the shape, the size, the data type, all of that. This might be a sphere. It might be a chunk of data inside a particle data set. It might be anything. And so we have to write it neutral to that. But it will always respect this protocol. It will always be able to access things like this. Field, in contrast, is much more restrictive. Field is very specifically an instance of a derived field object. And almost always, not always, but almost always, you never need to access this. It's provided so that in case you want to write generic functions that do different things, or if you want to do some very specific things that are uncommon, you can access it, but almost always, you'll never access this. You'll almost always access just data. So if I were to write a function, def dinosaurs field data, and I wanted to return the right value, I would say return data gas temperature times data gas density. So in principle, I could right now call this dinosaurs, and we'll just give it none and dd here, and it'll return that for me. And you'll see it gives me the exact same set of values.
Sorry, I must have followed along wrong because my gas has no temperature.
Oh, well, let's go back up here. I had to make a second data set
Oh, you
object.
did add temperature to that. I
Yes,
see.
I did. I'm sorry.
No.
I should have called it something different. Why don't I do that? ES2. If we do this 7 more times, it'll be amazing.
So just assign.
Here, I'll leave this up for a second. And this is one of the downsides to
This feels like magic. We just got adding.
7 more times? 4, 5, 6, 7, 8. And so this is clunky. We don't want this, right? What we can do is we can register this function either with YT or with the data set and say, this is that derived field. The simplest way to do that is to call ds.addField. And actually, that needs to be ds2 in this case. So you can call on your data set the add_field function. Now, if we look at this, there's been a concerted effort among a lot of people in the YT community to improve and make the doc strings useful. Add field, we call help on it. You'll see that it takes a name, a function, a sampling type, and then it adds it as a derived field. So we're going to add a field to it. So let's give it a name. Gas dinosaurs. We'll give it a function. That's _dinosaurs, because remember, that's what I called it when I defined it. And then we have to give it a sampling type. Now, the sampling type doesn't always factor in, but what it does is it allows you to specify something like, is this field defined everywhere, or is it defined at discrete locations? That's the principal difference between these different sampling types. Is this a volume filling field, or is it a field that is defined at specific locations? The main thing, if I'm remembering correctly, that impacts is what shape it's expected to arrive. So we'll say that our sampling type is cell. I can never remember the distinction between cell and local if one exists. It's like I'm not alone.
I always say local.
You always say cell? I'm not even sure I use it. Okay. Well, let's do cell. No, let's do local. Think local, act cell.
Act cellular.
Cellular, yeah. And so now we added that field. So this is where things get a little sticky. If we look in DS2 fields now, check it out. Dinosaurs shows up. So now DS2, we'll say, we'll define a new DD equals DS2.R everything. And if we do DD.mean dinosaurs, it returns to us our average value of dinosaurs. It's so convenient that it's equal to approximately 1/2 times 1/2, or the mean value of 1 times the mean value of the other.
Do you want to say something about what ds.r is?
Yeah, I've been using ds.r a little bit in here. It's a slightly faster, slightly more terse way of describing data selections that are rectilinear. So I think I don't want to distract too much from things, and so I should have said all data here. But ds.r is a slice-based way of describing subsections of your data. Like here I could do colon, so that'll give me everything along x, colon, everything along y, but only at 0.5 and z. And then that becomes a slice through the domain. And then I could plot dinosaurs, for instance, and it gives that to me. Although I think I was supposed to wait for Chris to show the first plot. So now, because this is defined as a function, it can be decomposed. So Corentin showed how, it like when you do the chunks, it only applies it to the ones that are, or when you do derived quantities, it only applies it to one chunk at a time. And so it reduces the overall memory overhead. by defining this as a function that is neutral to the shape of the data that arrives or the size of the data that arrives, this can now also be decomposed across processors, across chunks, and so on and so forth. So we're building out sort of this mechanism of thinking at high levels. We're not thinking anymore about our individual arrays. We're thinking about the symbol manipulation here. Right? Who was it? Somebody really wanted to implement like a preprocessor step so that you could write this. Might have been Corrington in YAML, like use Unicode. So you would just write row times capital T and things like that. But we definitely did not do that. Do any of you use Unicode symbols for variable names? Or?
ASCII is Unicode.
Well, okay, ASCII's Unicode, yes. Like UTF-1. No? You can, like a Unicode snowman for you.
It feels like it would be more robust across different codes.
Yeah, it very well could be. So let's say snowman equals. Yeah, okay. I remember, this is why I didn't do it, because Python has so many restrictions on which ones you can use. They don't want anything that's too confusing. But there are, as long as I'm going down this road, actually, one thing you should be careful of, and we've run into this in YT, is using Unicode, but there are multiple different glyph numbers that can sometimes resolve to the same symbol. So one fun thing is that mu and micro are different Unicode code points. And so they happily resolve to the same glyph, but they are not the same. So anyway, back to derived fields. And was I only supposed to go until 2:30? 2:30. All right. So this is how we define derived fields with cell data, okay? There are additional ways to define derived fields with respect to, say, particle data. So let's go back and let's take a look at how particle data loading works. So we have a second function, load particles. The way that load particles works is very similar at a base level to the way that loading uniform grid data works. However, there are some key differences. For instance, you still have to specify a bounding box, although it is now optional. Okay? If you do not specify a bounding box for a particle data set, it computes what the bounding box is by looking at the min and the max and the extent, and then adding on an epsilon. There are situations where you want to have a uniform bounding box, though, like for instance, comparing across time steps, and you want to be able to compare plots and whatnot. You want to make sure that you have the same bounding box for all of them. But the bounding box also is largely just for the indexing, for the purposes of indexing. So let's say that we wanted to load our particles. Let's say now we have particle X, np.random.normal this time. And let's say that we wanted 64 cubed particles. We'll do particle Y and particle Z the same way. And we'll do particle mass is equal to np.random.normal. And in this case, we want it to be 64 cubed, but it might take the location first. It does. Okay. So it takes location, then scale, then size. So we'll do location here. We'll let be 0, 0, 0. Here we'll make our location equal to 0.25. And then we will make our sigma equal to something very small, 0.5, let's say. Not sigma?
No.
Scale?
Scale.
Okay. So now if we look at particle X, see it goes to -4. So I think we should be safe if we do -5 to 5. Okay. We're all in agreement that if anything goes wrong, I'm not taking the fall. So we're going to go ahead and we're going to call these particles, we're just going to let it assign the names to these particles. Okay. There is one really fun thing about particles that you don't get nearly as much with grid cells, and that's having multiple different particle types that sort of overlap. Like you often, it's not as common to have multiple different fluid types that overlap, like having two different densities defined in the same place for a fluid. But with particles, because they're discrete, because you've got different classes of star and dark matter and whatnot, you can do cool stuff with the field types a lot more. So here we'll say particle position X is particle X. Particle position Y is particle Y, particle Y, particle Y. And now we make sure, let's see, I'm gonna call this DS3, getting closer. We'll say B box is equal to an NP array, -5 to 5, -5 to 5, -5 to 5. Failed. Mass is not defined. Oh. Here we go.
So with the bounding box, you have to basically make it big enough so it's safe, or would it basically trim out particles?
It'll trim.
Okay, so like it won't throw errors.
Right. Yeah.
And what if like you're comparing time steps and a particle re-enters? Is it gonna be assigned like the, let's say like, you know, in time step 1, you have some particle with some index.
Yes.
And it gets trimmed in like 2 time steps, and then it kind of re-enters like some sort of, I don't know, really elliptical orbit, right? That
Right.
comes back. Is it gonna be assigned the same index or just?
So typically the index will be from the code.
Yeah, okay.
So in that case, it will retain whatever the code says the index is, but it would not have the same position in the array.
Okay.
We don't make as many assumptions about or we make assumptions about intra time step ordering of particles, but not inter time step ordering.
Thanks.
So we do though, one thing we do provide is we provide a 64-bit Morton index to the particles if you want to do comparisons. And we do that sometimes for like assigning particles to cells and whatnot. But it's a little tricky to use.
Yeah, that's a pretty specific, I think, use case.
Yeah.
Yeah.
But we'll get to it. I like that. Okay. So DS3 now, we look at all data. We can look at our field list, or let's just look at fields. Now you'll note there's an all here, which has these in it: deposit, gas, index, IO, n-body, and stream. That's way more. The way that YT thinks about particles, by virtue of the fact that they are variable length arrays, is that each class of particle is assigned to a different particle type. And by default, it's what's called an n-body type. It's kind of a silly name in that it's like content free, basically, right? They're all n-body. But the n-body particles are the default. All is a concatenation. It's a special term for concatenating all of your particles. So with derived fields in particles, you can specify if they apply to just one particle type, they apply to all particle types, and you can also construct particle unions and particle filters. So let's experiment with that a little bit. here we have DS3. And we have particle fields by type. This shows me all the particle fields. Oh, the index hasn't been generated. Oh, particle fields by type IO. So IO is the on disk, particle mass, particle position. Now if we do ds3.derived field, derived fields list, see we've got all of them. We look at DS3, we can see particle unions. Oh, and it looks like we don't have particle filters unless we define them. But these are the particle unions. So in this case, we've got all, which is a particle union of IO, and n-body, which is a particle union of IO. So let's go back up here. And let's add on. We'll make DS4. If I called them Babylon, then we'd already be at something interesting. But I guess we'd have to stop after the next one. And in this case, we'll have particle position X. We'll call it DM for direct message or dark matter. We'll do another DM. 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 Now, and we will come back and modify this in just a second. I just want you to see what this looks like. Now, instead of IO, we have DM. All the fields that we had before are now dark matter type. So if I do ds4.alldata, dd.mean, DM particle mass, it comes out to exactly the location that or almost exactly the location that I specified. So before we move on, I want to note here that this was a purely cosmetic change. All I did was add a field type to the name of my field, and that field type was named DM for dark matter. Let's do something cooler. Now let's have galaxies or some stars. We'll say stars X, np.random.normal. And this time we'll specify location is 0.7. Sigma equals 0.
Scale.
Yeah, it's scale. And actually, let's make that 2.0. Scale equals 0.25. 1. Will that still stay inside? No, let's do 0.5. I'll do this for Y and Z. This location, we'll put it in the plane in Z. But we'll put it outside in X and Y. And we'll make it a little bit more distributed in Z. Okay. And now we'll do a mass. No, man. Let's make this a location of 10 and a scale of 5. And now let's add on a new value. Well, this one will have uniform. I got to add size here. How many stars do we want? How about 16 cubed? Okay, we'll scale it up by about a factor of 10 to the 5. So now what we can do is we can load in new item. Do stars, particle position X goes to stars X. Same for Y and Z. Now let's add on stars, particle mass. And we'll call it age. Okay. So I'm going to give you a second because I realize everybody is typing, and I know that if you're typing when I'm typing, you're probably not like exactly where I'm at. And I want to make sure we're at least, if you want to, that you can catch up. So this is no longer a cosmetic change. Now we've actually added on a new set of particles. And the particles are of different size. So the other ones are 64 cubed. These are 16 cubed. So that's like a 60 factor of 64 difference, right? 4 cubed. Yeah. So now we load it and we can look here. You'll see we've got all in there. Also got DM for dark matter. So far, so good. And then if we look at stars, oh, check this out. Stars has an additional field, age. And if we look over here at all, it does not have age. So the way that particle filters and particle unions work in YT is that any field that exists across all of them can be accessed from the union. Any field that does not exist across all of them cannot be accessed from the union. So the built-in all union will only contain fields that are well-defined everywhere. So it won't contain age, but it will contain mass. DM also no age. Stars contains age. And if we look at these here, so now let's do DD equals DS for all data. DD.mean, let's do extrema. And if we look at the extrema of DM, particle mass, min of particle mass, and max of particle mass, it gives us those. And then if we do the exact same thing with stars, gives us those. That's fun. It's an infinite source of energy. But now if we look at the union of all, you'll see that it computes it on all of them. And if we try to access something like all age, it'll throw an error. We'll say that could not find field all age in particle data. Did you mean stars age? It's not always true that you'll have access to all of the different information a priori. So some types of code, for instance, store things like particle type as a discrete field. And so for those types, you can define what's called a particle filter. And there it's add particle filter. Filter here is a function. Anything that it returns true on will be the accepted particles. And so you could say, for instance, I just want old stars and supply a filter that only returns old stars. Okay. There are more advanced things that we can do with derived fields. For instance, I showed how to do ds.addField. There is also, and that works after you've already created a data set. But you can also do yt.addField. it takes the exact same arguments, and any subsequently loaded data set will attempt to add that derived field. The downside of using yt.add field is that it does not get added to any existing data sets. So anything that's already been loaded does not get that new field added. There are also a couple different, and we'll go into more detail on some of these at a later time. There are also add gradient fields to data sets. What add gradient fields can do is it can either take one or multiple fields for which it will attempt to compute a gradient and then add all of those gradient values on. So we saw that density got added on as a gradient. But if we return to our earlier data set that we added dinosaurs to, which I believe was DS2, and we look at fields, we'll see we've got dinosaurs, but we don't have dinosaurs gradient. So let's do ds2.add gradient fields. We'll call it gas dinosaurs. It adds them on, it returns to you the names of all those fields. And now if we look at ds2.fields, see there it is, dinosaurs gradient magnitude, dinosaurs gradient x, dinosaurs gradient y, dinosaurs gradient z. I'm not going to cover it in detail. However, you can also add on spatial fields. At present, we've looked just at the, and we will cover this, just not in this particular dinosaur eating moment. You can also provide some information to your fields through what are called field parameters. They're really brittle, but you can provide them. That allows you to specify things like an orientation for a disk in order to get like radial bends out along a non-axially aligned disk. It allows you to, so like you could get a theta and a phi coordinate from a non-axially aligned sphere, for instance, by providing field parameters, but they're a little bit brittle to define. You can also apply spatial operators. So doing 1 or 2 or 3 consecutive cells along different dimensions, being able to apply it along 3-dimensional arrays. So like if you wanted to take a moving average, for instance, you could do that by requesting what are called spatial buffer zones. I'm going to show how to do the field parameters, and then I'm going to turn it over to, is it Chris?
Coffee and then Chris.
We can just skip the coffee, right? I'm going to say DD equals our original data set dot all data. And if we look at ds.fields again, you'll note here in index, check it out, there's stuff like cylindrical radius, cylindrical theta, cylindrical z, right? And if we look in there, here, oh, check out that source code. Look, it's getting a field parameter. What you can do on your data object, you can specify a field parameter. You say set field parameter, and I'm going to say that my normal here is going to be 0.5, 0.5, 0.5. And now if I do DD index cylindrical theta, it gives me these values. Now I'm going to clear data. Now I'm going to set my field parameter normal to 0.1, 0.2, 0.3. I hope that this one. And now when I access the cylindrical theta, it computes a different theta because it's using a different normal vector. So the way that this is designed to work, let's say you've got a simulation where you've got a non-axis aligned disk. I don't know if that ever happens. You set your normal. Oftentimes you'll even be setting this normal based on some programmatic calculation like the angular momentum vector, which you can get from the derived quantities that Corentin described. And then you could do something like binning it based on the theta, the r, the phi, all these different things in order to compute different field values along different axes and whatnot. The other thing you can do with this is you can also specify, like if you want to apply a normal transform or like an affine transformation or something like that, you can write your own derived field to apply or unapply that. The same thing works with particles. You can specify center and a normal. Then you can get things like the particle theta, particle, what's it called? So that is a basic introduction to derived fields. All right, let's get some coffee.
Hey, thank you, Matt. Yes. Well, let's go get coffee, and then when we return at 3, we will do some plot.